Okay, our final talk in this session is by Deane, and he will be talking about hot topics in cold acoustical oceanography.
All right, thank you very much. I'd like to start out by thanking all my colleagues who provided me with slides for this talk. I'm being quite bold in presenting other people's work. I've gone over the slides very carefully, however, and if you have any questions at all about those slides, I'll be very happy to pass that on to my colleagues. I would also like to thank Anthony Lavery, who spent some time with me on this talk to improve it. So why interest in the Arctic? The Arctic is very sensitive to climate change, we know that. It's a region with resources, with gas, with oil, with minerals, and so it's of economic and cultural interest. And it's a region of strategic interest. And so it's working up there is also a national security issue. And acoustics has a lot to offer in terms of studying the changing Arctic environment. And my intention is to give you an overview of some of the hot acoustic things that are going on in this cold region. Here are a list of topics that I plan to cover, and the colleagues who provided me with this information. The first two really have to do with the larger underwater soundscape, looking at acoustics on very long scales, tens to hundreds of kilometers. And then I have a very specific sensing technique that I'll go over, high frequency acoustics looking for oil spills by Andoni. And then the underwater ambient noise and how can that be used and exploited in the Arctic. Aaron Thode has given me some data that he's been working on tracking marine mammals. And finally, I'm going to end with some work using the underwater soundscape in the bays of marine terminating glaciers to understand glacier dynamics in Svalbard and Greenland. So starting with Peter's slides. Peter's right here, he can correct me if I make too many mistakes. Peter's done, and his colleagues have done something that I think is quite remarkable. They've deployed a drifting vertical line array pretty much at the North Pole and let that drift along the prime meridian for about 4 or 5 months and collected acoustic data from this deployment. They're working on the Thor hypothesis, the idea that as the Arctic ice retreats, there's less multi-year ice up there. So the interface between the ice and the ocean is going to change. Pressure ridges are going to change for young ice as opposed to old ice. And it's going to change the scattering and propagation of sound under the ice. Moreover, the sources of ambient noise from that ice will be decreased. So as Peter has summarized on this slide, there are certain things that one would expect from changing ice cover in the Arctic. And indeed, when one looks at some of the data from the deployment, one finds that some of these shifts are actually occurring. I guess this is an historical ambient noise power spectral density estimate here. I guess this is from Iredar in 1984. And the crosshairs give you a fixed reference point between both plots. And you can see that this peak in noise level sort of around 10 hertz has shifted slightly to the right, but also decreased significantly since 1984. So the ambient noise environment up there certainly is shifting and changing over time, as one might expect. Now I have some work by Art and Henrik, and they're looking at duct propagation in the Beaufort Sea. Art and Henrik have been running propagation simulations to look at propagation in these ducts that form in the Beaufort Sea, and Their data is based on profiles gathered from these ice-tethered profilers that have been developed by John O'Toole at Hui. These instruments have, as Art says, provided many profiles from the Arctic. And I guess they're also being used by the former Soviet Union, by the People's Republic of China. They're open access, and Art and Henrik have been exploiting this data to understand long-range propagation. Here are some examples of temperature and salinity profiles. These ducts in Beaufort Sea evidently are persistent from year to year, and there's warm water riding on the thermohaline, the heliocline boundary, which creates this subsurface duct. And this has important acoustical consequences. Any sources in such a duct are isolated from the ice from above, and the sound is trapped from below. So here are some simulations that Henrik and Art have done. These particular simulations were done using Oasis. And on the left-hand side, you can see a typical Arctic profile. The source is placed within where the duct would be if there was one. And you can see here that over 100 kilometers of range, you don't get much sound transmission at all. However, in the presence of a duct, significant energy can be trapped up near the surface. This energy doesn't interact with the ice field over the top and can therefore propagate long distances. There's a frequency-dependent effect here. The cutoff frequency for the duct is around 300 hertz. So lower frequency energy isn't trapped in the duct. As frequency increases, absorption of sound in the water column starts to cut in. And you can see here in the inset the difference between 450 hertz and the wider plot was done at 900 hertz. And variability of sound within the duct is about 10 dB, depending on receiver location within that duct. Here I have a very different kind of study done by Andoni Lavery and Chris Bassett. The idea here is that as the Arctic becomes explored and exploited for its energy and mineral resources, we can expect more environmental problems. And with ice up there, how are we, for example, going to detect ice spills that can be trapped underneath the ice? And Andoni is looking at this question using high-frequency backscatter sonar. An experiment was done at CRREL where artificial ice was generated. You can see here the experimental setup. There's an air, ice, oil layer, and multiple frequencies were used to investigate the structure of this boundary. And the data are very interesting. On the left-hand side, you can see what you're looking at are contour lines of a matched filter output for the high-frequency sonar pulses that were transmitted and received as a function of time and range. And on the top plot, you can see how a sonar pointed at a fixed point in space, how the return changes over time as the ice freezes. And the vertical striations are thought to be real, and the presence of, indicating the presence of the formation of brine channels in the ice as it freezes. If one moves the sonar underneath the ice cap, you can get an idea of the spatial inhomogeneities in the ice, and again you see evidence of these brine channels being formed. When oil is released under the ice, and with a particular experimental setup that Andoni had, the ice formed this cap, which was very convenient for containing the oil that was released. And sure enough, you can see a very distinct oil layer, which can be detected by the high-frequency sonar returns, which is encouraging. It shows that this is a a suitable means for going out and looking for oil spills. One can imagine a sonar on the top of an AUV cruising around under the ice looking for oil layers. But also one can learn something about the dynamics of the freezing water if there is no oil present. These data were provided by Aaron Bode, and Aaron is looking at the underwater ambient noise scape. So rather than using active sources, one of the interests of members of the Acoustical Oceanography Technical Committee is exploiting natural sounds that occur in the ocean. One of the benefits being, of course, that presumably they don't interfere with the marine mammals that like to hang out in the ocean. And one can learn a lot by listening to underwater ambient noise. Aaron is involved in a program that exploit these directional autonomous seafloor acoustic recorders, the DASAs. And I believe this, as you can see, there are a lot of these arrays that have been deployed, and I believe they're funded by Shell. Is that correct? Yes, by Shell. To presumably with the intention of monitoring sound levels as they go out and explore for oils and minerals. But Aaron has been seeing what can be done with these extensive recordings. Each one of these array elements contains a hydrophone, but also a vector sensor. So each array element can not only detect the pressure field, but also the velocity field of the incident noise. And from that, you can make estimates of the incoming direction of the sound. And you can do some pretty interesting things with this, as Aaron has done. Let me explain what these curves are. If you take a segment of noise from the recorder and turn it into a power spectral density estimate as a function of angle, which you can do with the vector sensor, you then get angle versus frequency. So these are angle versus frequency plots, but organized into the overall energy in that particular segment of noise. So the plot at the very top is for noise intensities that lay between the 0th and 10th percentile for the overall record. In the middle, it's the 40th to 50th percentiles, and at the bottom, it's the 90th to 100th percentiles. And you can see on these plots that the directional density function for the noise field, and what you're seeing here in color is the number of records that match that particular angle at that particular frequency in that category of sound intensity. You can see that the directionality of the noise field itself is quite sensitive to whether it's a low intensity arrival or a strong arrival, a weak arrival or a strong arrival. Across a broad band, the low arrivals tend to come in from the north, no matter what the frequency, which is a pretty interesting result. As you get to the more intense noises, you can see that there's a distinct change in the angular spread of the arrivals. And in the slides that Aaron gave me, he pointed out that one can actually form an underwater acoustic compass this way. If one orients oneself off all the low frequency arrivals, one knows which way is north. But I think, this is another view of the same data, if you like, but using a multi-year analysis. So what you're looking at now is if one picks up the peak arrivals here, where it's very red, almost dark, and plots those trajectories as a function of year, you get these three plots. And you can see that there's a lot of interannual variability for the intermediate and high intensities, but the low intensity noise is always predominantly coming from the north. And this last slide, I think, is particularly interesting, and it's an example of what can be done with this kind of data. What Aaron is showing here is the passage of a storm at 300 hertz in frequency and angle space. And that is, in a way, the grand challenge of this ambient noise oceanography. It's one thing to put an array out and listen to the noise, which is from all different kinds of sources: anthropogenic, biological, ice, breaking waves, ice wave interactions, seismic events. It's one thing to listen to that. It's quite another to understand what it is and what its significance is in terms of the overall Arctic environment. And here Aaron has shown a beautiful example of how one can, for example, detect the passage of a storm, generating noise at 300 hertz. And finally, I'm going to give you some examples of ambient noise oceanography in the bays of marine terminating glaciers. And here what we're trying to do, and there are really two groups of us doing this. I'm one of the people interested in this endeavor, along with some colleagues from Poland. And Erin Pettit and some of her colleagues have a separate program looking at these effects. And the motivation here really is to understand the stability of the Greenland ice cap, which contains up to 20 feet of sea level rise locked up. And the connection between that ice cap and the ocean are the marine terminating glaciers. And as you can imagine, with the more rapid retreat of these glaciers, there's a lot of interest in trying to understand what controls their carving dynamics, for example, and their flow to the ocean. And we collectively are trying to develop new acoustical techniques to do this. There are many well-established techniques for studying glaciers, in situ instrumentation on the glacier, satellite observations, seismometers, and so on. But they all have limitations of one kind or another. And satellite observations, for example, work as long as there isn't cloud cover or it's light up there. And of course, there are extensive periods of time it's not light up there. So the great goal here is to measure, quantify, and understand the underwater ambient noise field in these bays and interpret it in terms of the ice and glacier dynamics. And I've given here just a smorgasbord of different physical processes that generate sounds. There are icebergs floating in the water, they're melting. Those melting icebergs generate a lot of sound. I think I'm getting a time. Yes, okay. It's all right, I'm almost done. So here is a slide. Okay. Unfortunately, we have a technical difficulty with some of the media on these slides. However, at the end of this time, I have exported the videos, and I'll see if I can play them separately. What Aaron had shown here is bubbles being released from ice and the sounds of those bubbles. And they make interesting popping sounds that one can hope to use to measure ice melt rates. Erin and her colleagues have also done some very interesting work on subglacial discharge, which evidently radiates noise in sort of the 50 to 150 hertz band, and which is extremely difficult for the glaciologists to quantify. Nobody wants to get up to the front of these marine terminating glaciers for the fear of blocks of ice falling on their heads. So it's quite difficult to quantify these flows. Finally, as another example of what can be done, my colleagues along the bottom here and myself, we have discovered that it is in fact possible using underwater spectrograms to determine the mode of carving from these glaciers, whether it's sliding, subaerial, or submarine blocks of ice floating up to the surface. Each of these events has a unique signature. And in fact, from the intensity of the sound, it's possible to actually estimate the size of the blocks of ice. This works, I think. So those explosive sounds you can hear are bubbles explosively bursting out of the melting ice in the fjord. finishing here with a breakdown of exactly what the acoustic spectrum and time signature looks like from those exploding bubbles. The point of the lower right-hand graph is that the whole process is extremely sensitive to depth. So as you can imagine, hydrostatic pressure alters the amount of free energy available for creating sound as the bubbles explode out. And so we're really in the bay only listening to a thin layer of melting ice near the surface. And then, if I can, let's see if this works. Yeah, okay, good. And what you'll see here are slow motion videos. The interframe interval here was half a millisecond. So this is a very rapid footage of what that process looks like. You used to be able to buy seltzer birdie. People would take the ice and put it in their drinks because you can hear it crackle and fizzle and pop. And when I was up in the Polish polar station, I became the resident expert on the right kind of ice to put in your whiskey so it made the right kind of sounds for maximum enjoyment. And here we go. These are Erin's and her colleagues' slides. And that concludes my talk. Thank you very much.